Okay, so do you have any questions before we start? I mean, on last lecture we had started kind of reviewing some of the mathematical tools that we will be using. We discussed the vectors and the generalization of the derivative to a three-dimensional case. We had seen the gradient operator. And the gradient operator, we said that it behaves like an ordinary vector in terms of multiplying a scalar function, multiplying with a vector function. We had the scalar product, which we call the divergence, and also the vector product, which we call the curl. And the definition of the divergence of a scalar function was, we had defined it through this relation, now the gradient of a function. So if you just take 2 points very close by that are separated by dl, then the difference of a function u evaluated at these 2 points is related to the divergence of that function. And also, as a vector, the divergence of a function also told us the direction in which the function increases the fastest. And then we had the curl of any vector field, which was defined by this vector product, and the divergence of our vector field, which was defined as the scalar product of this gradient operator and the vector field. So that was basically where we had left. Now, any questions on these? Now, today we will start with can we have kind of a physical intuition on what these are, what the curl and the divergence are, and then continue with probably the Dirac delta, and kind of that's it. Now, any questions? Now, from one-dimensional case, you already know that if you have a function, if you take its derivative, integrate it over a region, A to B. Well, this is nothing but the difference of FB minus FA. Well, this is called the fundamental theorem of calculus. Well, in 3 dimensions, we can basically do the same thing. So if you have, for example, if you have a function u, you take the derivative. Well, this time the derivative is the gradient of u, integrate it along a path from, let's say, point P0 up to P1. Then just like in the one-dimensional case, this is nothing but the value of that function at P1 minus the value of that function at P0. Let's look at the other ones. This time let's take a vector field. Let's take its divergence. This is just a number. We can integrate it over a volume, an arbitrary volume, V. And this we can write as a surface integral, where, okay, let's say this is our volume V. This is the surface of the volume, which we will use this notation. Del V is just like kind of a derivative. So if we have a volume integral, we can convert it to a surface integral over the surface at that volume. Well, in a sense, these 2 expressions, the one-dimensional case, and this one, they mainly state the same thing, in the sense that if you take a line, just a straight line, what is the boundary of that line? The endpoints. So integral is nothing but the summation. So this is the summation at the endpoints. So this is an integration at the endpoints of this line. So we have a one-dimensional object. The integration at the endpoints is just the sum of 2 points. Here we have a 3-dimensional object. the boundary, the integration over the boundary is the surface. This closed surface. This is a closed surface. Now, if you remember the Gauss law in your first year, this will be, we will use this in the Gauss law to express the Gauss law. Now, just again, remember the Gauss law. Just take a point charge. We already know that the electric field of a point charge plus Q, it is radially outward. We know that E dot ds over the boundary, this was equal to 4 pi over epsilon 0, 1 over epsilon 0 times Q enclosed. This was the Gauss law that we had derived in the first year. Now we see that we can write this as divergence of the electric field over the volume, which basically, well, we are changing the left-hand side. We are not touching the right-hand side. So this basically tells me that for such an electric field, the divergence is non-zero. Well, if you look at this electric field, the lines are kind of diverging from a given point. So this is what, more or less, what this divergence means. If the electric field, the divergence of an electric field is non-zero at a given point, it just means that there are some sources of electric field or any other vector field at that point, and the electric field lines are kind of diverging from that point. Now let's look at the magnetic field. If you have a current carrying wire, a straight infinite wire, we had studied the magnetic field, if you remember it, this is how the magnetic field lines will look like. And B dot dl, B dot ds on this any closed surface would have been equal to 0. In a sense, it makes sense because we said that the divergence is kind of the source of the field lines. Well, there is no source of field lines. There is no single point from which the field lines are coming out. So this is equal to divergence of B evaluated on the volume. This is equal to 0. So we already have one of the differential form of one of the Maxwell's equations. So this should be 0, whatever the volume is. So it basically tells me that B should be equal to 0. Well, this equation is the same thing as the above integral equation. This is the integral form. This is the differential form. Well, the magnetic field we will study in more detail in the second half of the semester. So this is the divergence. In a sense, it measures how much if you imagine the vector field as a kind of a flow, it measures whether there are new sources at a given region or sinks. If the divergence is negative, it means there will be sinks. If it's positive, there will be sources of the field line. Now let's look at the curl. We have this expression, curl of any vector field. We can integrate it over a given surface. This is any surface that you can imagine. This is equal to the integral of the vector field over the boundary. Well, if you imagine any surface, so this is the surface S, this is the boundary of S. If you have any surface, the boundary is a closed loop. So the curl of a vector field over any surface is equal to the loop integral of the vector field around the closed loop forming the boundary of the surface. And again, if we go back to the electric and magnetic field analogs, B dot dl over a loop, if you remember, this was equal to mu0 over 4 pi times the enclosed current. Now, in particular, it was, if you go back to this example over here, so the B dot dl around this loop is just I, but the integral of B dot dl, we can write it as the curl of B over the surface. Well, if you look at this magnetic field lines over here, the magnetic field lines are curving around this loop, around this point. All the magnetic field lines are curving around this point. So that is basically what the curl measures. Curl measures whether a given magnetic field is rotating, in a sense, around the given point, or how much is it rotating. If the curl is non-zero, it is rotating around that point. If it is zero, then it is not rotating around that point, in a vague sense. The analogy is not perfect, but it still gives an idea about what's going on. Now, the curl. Now, in this example, we said that the curl of B is non-zero. Now, if we go back to this example, the electric field example, E dot dl around any closed loop in electrostatics, this was 0. So which tells me that curl of E is equal to 0 in electrostatics. Because in electrostatics, we know that the point, at least for a point charge, the electric field lines are radially outward. They are diverging from that point. They are going away from that point. And they are not rotating around that point. But when you look at the magnetic field lines of an infinite straight wire, it's not diverging from any point. It's not starting, it's not ending. So that's why the divergence is 0. But it is rotating around this point. So its curl is non-zero. Curl, in a sense, measures the rotation of the field lines, in a sense. Now, let's look at some coordinate. Any questions on this one? Now, we will be using these ones all the time. So in the first year, if you remember your first year course in electromagnetism, the course was based on integrals. Everything we express in terms of integrals, the surface integrals, loop integrals, line integrals, etc. This year, we will be expressing everything in terms of derivatives. So already here we have one of them. Instead of B dot ds equal to 0, we will just say that the divergence of B is equal to 0. Well, these are the first derivatives. Then, of course, we will meet many other second derivatives. We will see expressions like, okay, we had the gradient of phi, which is a vector. We can take its derivative. Well, we can do it in two different ways. We can talk about the divergence of the gradient, or we can talk about the curl of the gradient. This is one way. We took the derivatives of vector fields. We can take the divergence of vector fields. Well, this is just a number, a scalar function or a scalar field. Now, in this course, whenever we talk about fields, what we mean is just a function whose value who is defined at everywhere, whose value can be a number, a scale, a vector, etc. So when we say a vector field, it's basically a function defined at every point in space, but at every point, its value is a vector. A scalar function is again defined everywhere in space, but its value is just a number. Now we have a vector field. We can talk about its divergence, which is a scalar function, scalar field. A scalar field, we can talk about the gradient of a scalar field. we can talk about the curl of a, no, sorry. So that's, we can only talk about the gradient of a scalar function. There are no other way. We have the curl of a vector field, which is itself a vector field. We can talk about its divergence, or we can talk about its curl. So basically, these are the 5 combinations that one can think of. The second derivatives. Now, the first one. Now, let's look at the first one. It is the divergence of the gradient of phi. Now, we had already defined the gradient of phi. This is the divergence of, in the x direction, del phi by del x. In the y direction, del phi by del y. In the z direction, del phi by del z. This is a vector field. We had talked about the divergence. It's just like the scalar product of two vectors. The x component of this one is the derivative with respect to x. The x component of this one is this one over here. So basically, we have the, if we multiply the two, we have the second derivative of phi with respect to x. The y component of this vector is the derivative of phi with respect to y. The y component of this one is the derivative with respect to y. So if we just multiply it, it's the second derivative with respect to y. And similarly for the z components. The z component is the derivative with respect to z. The z component is the derivative of phi with respect to z. You multiply them, you get the second derivative. Which we usually write in this form. We define another differential operator. This is our definition. It's called the Laplacian. Most of the semester we will be dealing with different methods of solving differential equations that contain the Laplacian. That will be, we will be devoting most of our time to solving Laplace equations or the so-called Poisson equation. And so this is, the definition is the Laplacian of phi. If you come to this one, well, that is 0. Let's try to see that it is actually 0 explicitly. For that one, I will be explicit. Curl of the gradient of phi. Let's look at one of the components, the x component. We have two vector products. The x component is the y component of the first one times the z component of the other one, minus the z component of the first one times the y component of the second one. So it's the difference of these two second derivatives, but as long as phi is a sufficiently smooth, nice function, you can just change the order of the derivatives. But if you change the order of the derivatives, these are just equal. So this is equal to 0. And if you look at the other components, again, it will be 0. So although we can formally write such a second derivative, when you evaluate it, it will always be 0. So we don't need to worry about that. Well, for this one, well, there's no simplification or special definition for this one. We don't usually end up having such a operator, so it just stays. If you look at this one, it is also 0. So the divergence of a curl of gradient is 0. the curl of a gradient is 0, the divergence of a curl is also 0, as long as A is sufficiently smooth, which is almost always the case in physics. And finally, we have this one. If you write it explicitly, that is, it becomes the gradient of the divergence of A minus the Laplacian of A. Again, this is just a term here. And here we have the Laplacian operator. So basically, in fact, we only need to worry about one second derivative operator. Two, let's say. One Laplacian operator, two this one. All the other derivatives, all the other possible second derivatives we can write in terms of those two.
Why don't you use gradient of a gradient?
You say gradient is defined to act on scalar functions, to give a vector field. So gradient of a function is a vector. You cannot take the gradient of that one. Any questions? Now let's look at different coordinate systems that we will be using. Let's start with spherical coordinates. Now, most of the time we use x, y, z coordinates, but it's not the most convenient coordinate in some problems at least. And there's nothing special really about the x, y, z coordinates. There are some simplifications. If you consider the unit vector in the x direction, it is constant. If this is my x direction, whether I'm here, that is my x hat vector. If I move here, that is my x hat vector, etc. Wherever you go, your x hat vector is the same vector. But if you want to choose a different coordinate system, that is also fine. Another coordinate system that we quite frequently encounter is the spherical coordinates. So let's first define the spherical coordinates. Now, the important thing in specifying coordinates is that if you know the coordinates of an object, you have to be able to tell uniquely where is the position of that object or event. Now, what we, in the x, y, z coordinate, what are we doing is, let's say, if this is our origin, this is x, this is y, this is z. If I tell you the x, y, and z coordinates of any event, I'm basically telling you to go this much in that direction and then to go this much in this direction after that point, and at the end to go this much in that direction. And then you will find your event. So that is what we mean by coordinates of an object. But instead of telling you that, I can just tell you that, okay, go 5 meters in that direction. That will also uniquely specify in which direction you have to go. But of course, the problem is, okay, go 5 minutes, it's easy to say and formally define. In that direction, well, that is somehow we need to kind of use the x, y, z coordinate system still. What we do is we choose the x, y, z coordinate axis. So this is my, let's say, the point at which end the event occurs. I consider a vertical on the xy plane. And then I consider a vertical towards the z-axis. This is vertical. This is vertical. So this is the, r is the distance of this event from the origin. Then to okay, this telling you r, I already tell you the distance, 5 meters. Now, to be able to tell in that direction, I need to tell you two angles. I tell you this angle, and I need to tell you this angle, which I call the phi. So basically, I say, okay, this is the z-axis. The direction makes 20 degrees with the z-axis. Okay, so that is 20 degrees. But nevertheless, it can be any of these directions make 20 degrees with the z-axis. So what I do is, okay, this is 20 degrees. I take the projection of this point in the xy plane. And on the xy plane, I connect it to my origin. And then tell you this angle over here. Okay, so if this is my x, okay, 20 degrees in this direction. And then rotate 30 degrees around the z-axis. Phi is 30. Theta is 20. Then rotate around the z by 30 degrees. Phi is 30 degrees. So that is how I define the theta and phi angles. And once I tell you what is the r, theta, and phi coordinates of an event, you know exactly where that event is, the position of that event. And these are called the r, theta, and phi, are the spherical coordinates of a point. You can relate it to Cartesian coordinates. You see, x, y, z uniquely specify the position of an object. R, theta, and phi uniquely specify the position of an object. So there should be a relation between them. And the relation is x is equal to r times sine theta. Well, r sine theta, if you look at this right triangle over here, theta is this angle, r is the length of the hypotenuse. It is this length over here, or this length over here. So if you imagine this right triangle over here, r times sine theta is the hypotenuse of this right triangle. If you multiply it with cosine phi, you get this length, which is the x-coordinate. If you multiply r sine theta by sine phi, you basically get this length, which is the y-coordinate of this point or this point. And the z-coordinate is just this length over here, and that is r times cosine theta. Or else if you want to go the other way around, if you take x squared plus y squared plus z squared, that is nothing but r squared. If you take the ratio of x over y, you get these cancel, you have the cotangent phi. If you take x squared plus y squared, square root, that just gives you r sine theta. You divide by this one, r's cancel, you get tangent theta. So you can just go back and forth between these two coordinate systems. Now these angles, okay, r and r is larger than or equal to 0. Now theta and phi, they're of course cyclic coordinates. So to define them uniquely, we restrict their values. What we said was, okay, so we started with the z. Theta is the rotation of this vector from the z. So we start from 0 and we go up to pi. Now phi is the rotation around the z-axis. So basically it's larger than or equal to 0, less than 2 pi. This is just the domains of definition of this r, theta, and phi. We don't allow phi to have the value 2 pi because 2 pi is basically the same thing as 0. So if you tell me a point, that point has a unique r, theta, and phi value. Well, kind of the only complicated, let's say, the singular point is along the z-axis, because along the z-axis, I mean, it doesn't matter which phi you choose. But that is something we will close our eyes on until it causes some problems. If you look at the position vector of an object, well, we can write it easily as it is r, the length, in the r hat direction. Well, the r hat direction is this direction. But now there's one thing you have to pay attention to. Let's say this is my origin, this is x, this is y, this is z-axis. If I'm looking at, I mean, we have been talking about vector fields. We will be dealing with vector fields. So at every point, a vector field will give us a vector at every point. And so at every point, we have to choose 3 coordinate axes. It can be x, y, and z. We can always choose it to be parallel to the x-axis, y-axis, and z-axis and call them x hat, y hat, z hat. That is one possible choice. Another choice is this spherical coordinates. For example, this r hat vector at this point, this is my origin, r hat vector is pointing in that direction at this point. If I go to this point, r hat vector is pointing in that direction. If I'm at this point, r hat vector is pointing in that direction. It points from the origin towards my point, just shift it to my point. So just keep in mind that this r hat vector changes from point to point. So it is actually a function of theta and phi. It is a unit vector. It doesn't depend on r. I mean, if I'm, let's say, here, r hat vector is pointing in that direction. If I'm here, r hat vector is still pointing in the same direction. It doesn't depend on r, but it depends on my direction. Well, we have to specify 3 unit vectors, not just one. R hat is just one of them. And the way we define it, let's just first note this thing. R hat squared. Let's take its derivative with respect to theta. R hat depends on theta. So in principle, r hat squared might depend on theta, so we can take its derivative. But in reality, it doesn't depend on theta, it is just 1. So its derivative with respect to theta is just 0. But I can take the derivative using the chain rule. So it's just twice r hat scalar product dr hat by d theta. So this basically tells me that this vector that I obtain is perpendicular to r hat. Remember, I'm trying to choose 3 orthogonal unit vectors. X hat, y hat, z hat, they are unit vectors, they are orthogonal to each other. Now I'm trying to choose 3 other unit vectors. But this time there's one complication. At least one of the unit vectors is constantly changing. It is different at every point, almost. So my other 2 orthogonal vectors should also change from point to point. But I have seen that this vector is orthogonal to that one, everywhere. So that's another possible orthogonal vector. Now, if you go out and calculate the length of that, the magnitude of that vector, that's a unit vector. So that is what I call, what I will define this as my theta hat vector. Okay, let me just correct one thing. I'm taking the partial derivatives. Now, why did I call it the theta hat? Well, let's think of x hat. Well, if I'm moving in the x hat direction, only x is changing. Y and z doesn't change. Well, that's one of the motivations why I call it the x hat. If I move in the y hat direction, only y coordinate changes. X and the z coordinates do not change. So if I move in the y hat direction, only the y coordinate changes. Or in another word, y hat is the direction in which only y changes. In this partial derivative, I'm only changing theta, I'm not changing phi. So this is the direction, this vector is a vector in the direction in which theta changes. Or if you go back to this picture over here, if we change theta, if we increase theta, this is my r hat vector over here. This is my theta hat vector. Well, I can just repeat the same thing for phi. 0 should be equal to r hat squared, its derivative with respect to the phi coordinate. Well, because r hat squared is 1, it's constant, it doesn't depend on phi, so its derivative is 0. On the other hand, I can just take the derivative explicitly. This will be 2r hat dot dr hat by d phi. So now I have a third vector which is perpendicular to r hat. dr by d phi hat is perpendicular to r hat. So I define dr hat by d phi as, what should we name it? Phi hat. Wrong. It's not a unit vector, dr by d phi. If you calculate its magnitude turns out to be sine theta. So this is a vector that is orthogonal to r hat with a magnitude of sine theta. And the remaining, the direction is what we call the phi hat. Again, this is the direction in which only phi changes. R doesn't change because it is perpendicular to r hat. Theta doesn't change because in taking this derivative, we didn't change theta. We only change phi. Now, if you look at this expression over here, it will be kind of complicated to show, but that is the direction in which phi increases. So it is kind of this vector over here. This is phi hat. So if you look at that expression over here, okay, r theta phi hat, this is my origin. At this point, this is the direction of r hat, theta hat, phi hat. If I come here, they change. If I go up, phi hat is pointing towards you. Theta hat is pointing almost towards you. If I go down, theta is almost pointing away from you. But whatever point you are considering, r hat, theta hat, and phi hat, they will be orthogonal vectors. They will be orthogonal to each other. And you can just use these three vectors to write down your vectors. Instead of the x, y, z components, you can talk about the r, theta, and phi components of your vectors at a given point.
Can you point out why there is a sine theta in front of it?
Well, let's look at this picture. What is theta and what is phi? Okay, I started from, let's say, the z-axis. I rotate by theta. Okay, so that kind of tells me that all these points on the circle have the same theta. Then to obtain the phi, okay, here I'm rotating this whole vector. Okay, then I'm rotating around z, around this axis. But if I'm rotating around z, I'm not rotating this vector, I'm rotating, let's see, this vector is rotating. Or when I'm rotating around z-axis, I'm basically rotating this length, this side over here. And the length of this side is r sine theta. So that is why I have this sine theta.
Peki hocam biz bu tetayet falan bunları x, y, z'ye nasıl çeviriyoruz?
Well, what is r hat? Let's start with that one. R hat is 1 over r x in the x hat plus y in the y hat plus z in the z hat. Right? What is x, y, z? Over here. So that tells you what r hat is in terms of theta and phi. Well, once you have the theta and phi, once you have the expression of r hat in terms of theta and phi, take its derivative with respect to theta, it gives you theta hat. Again, once you have its expression in terms of theta and phi, take its derivative with respect to phi, it should be proportional to sine theta. What remains is phi hat. Now, it will be a nice exercise, which I strongly suggest you to do. And once you have the theta hat and phi hat, you will realize that theta hat, that phi hat, this is also 0. theta hat and phi hat, I mean, up to here we only show that theta hat is orthogonal to r hat, theta hat is orthogonal to phi hat, but we didn't show that theta hat is orthogonal to phi hat. But if you calculate their explicit form, you can also see that they are orthogonal to each other. So these are the unit vectors in our spherical coordinates. Now let's do one exercise. What is the gradient in spherical coordinates? Okay, one way is, of course, just replace x, y, and z in terms of r, theta, and phi, use the chain rule, etc. So that will give you like 4 or 5 pages calculations. And if you don't do any sign mistakes, then you will get the result. Let's use this definition. We know that du is equal to gradient of u dot dl. Well, du will be u, the difference of 2 points. One point will have coordinates r theta and phi. The other point will have coordinates r plus dr, theta plus d theta, and phi plus d phi. So we have 2 nearby points. Their radial coordinates differ by a very small amount. Their theta coordinate differ by a very small amount, and their phi coordinate differ by a very small amount. This is our du. What we are trying to obtain is this one. So what is dl? Or dr? It's basically the same thing. We are just slightly changing the position. This is equal to the change in r hat. Well, the change, I have these 3 coordinates, so I can just take the derivative with respect to r, multiply with the change in r, plus take the change with respect to theta, multiply with the change in theta, and take the derivative with respect to phi and multiply with the change in phi. This is my dr. Well, let's see. This is equal to r hat doesn't depend on r. It only depends on theta and phi. So I don't need to worry about the derivative of r hat with respect to r. There's only this one. Its derivative with respect to r is just 1. So this is equal to dr in the r hat direction, plus, well, in spherical coordinates, r, theta, and phi, they are independent coordinates. So r doesn't depend on theta, so I can just take it out of the derivative. What remains is the theta derivative of r hat, which we call the theta hat. And here,
Why you said r is independent from theta?
well, you see, x, y, z, we say they're independent of each other. We can change x independent of y, independent of z. Similarly here, I can change theta without changing r or phi. In that sense, they are independent of each other. Of course, if you fix some fourth quantity to be constant, then when you change one parameter, you have to change also the other parameters to keep that parameter constant. But here we don't have that restriction. Plus, r is independent of phi. Derivative of r hat with respect to phi, we said that it was just r. Now here we have d theta plus r sine theta d phi phi hat. Now, this equality over here between du and the gradient of u, this relation, should be valid for all values of dl, as long as it is very small. For all values. If I take a special value, it should hold. If I take another special value for dl, it should hold. If I take a third one, it should hold. Now let's take some special cases. The theta is equal to d phi is equal to 0. So I have these 2 points which only differ by their radial distance. They are in the same direction. So then what we have, du over there, it is u of r plus dr, theta and phi, minus u r theta and phi. This should be equal to gradient of u, well, dot dl. dl is dr in the r hat direction. I can divide both sides by dr. So gradient of u, I take its scalar product with r hat. And this just gives me u of r plus dr, theta and phi, minus u of r theta and phi, divided by dr, which is nothing but derivative of u with respect to r. Well, let's look at the left-hand side. Here I have a vector. I'm writing this vector as r hat component, theta hat component, and phi hat component. If I take a scalar product with the r hat vector, it gives me the r component of this vector. So this is, let me write it here. I have this gradient of u. It has an radial component. And this radial component is nothing but derivative of u with respect to r. Well, we can repeat the same thing for which instead of, let's say, d theta is equal to 0, I can just set dr equal to 0 and d theta is constant. D phi is equal to 0. dr is equal to 0. Here dr goes to 0. Here d phi, d theta goes to 0. And just keep in mind, whenever I'm writing expressions of this form, I always have the limit that eventually dr will go to 0. Only in that case, this difference divided by dr becomes the derivative. But just to save some screen space, I'm not writing the limit dr goes to 0, etc. Well, if I consider this case, what will change? Well, here theta will be theta plus d theta, r will be r, here r theta phi. On the right-hand side, I will have the gradient of u multiplied with, remember, only d theta is non-zero, the second term above, the second term over there. And, well, just do the algebra. It's just one line. The theta component will just turn out to be 1 over r du by d theta. This 1 over r is this r over there. And if you look at the phi component, just repeat the same thing with d phi non-zero. Phi component will have 1 over r sine theta. D theta is equal to 0, dr is equal to 0, d phi non-zero. This will give me the phi component of the gradient of u, which will be 1 over r sine theta du by d phi. So in spherical coordinates, this gradient operator just becomes, in the r hat direction, it's just a derivative with respect to r, the first line. In the theta hat direction, it's just 1 over r times the derivative with respect to theta. Plus in the phi hat direction, 1 over r sine theta, derivative with respect to phi. So this is the gradient in spherical coordinates. I do advise you at least to attempt to derive this expression just using the relation between r theta and phi. r theta and phi and x, y, and z. You should eventually get the same expression, but after, let's say, at least 4 or 5 pages. Now, this expression, I'm not asking you to memorize it. Don't even bother to memorize it. If you need it in the exam, I will give it to you anyway. While you are doing your homework, you can just pick it up, look at it in your book. Well, there are similar derivations for the divergence and the curl in various coordinates. And if you liked it, I do recommend you to at least go over it in Appendix B of your book. So how to express the curl in various coordinates, the divergence in various coordinates. Again, here in obtaining this gradient in different coordinates, what we did was we only used this definition of the gradient. This is the definition of the gradient of a scalar function. We only use this one. To obtain the curl and the divergence in different coordinate systems, the only thing you need will be, well, this one. From here, using this definition, you can derive the divergence. And from this definition, on the first line, you can derive the curl of in spherical or in any other coordinate system. It also gives you an idea of how to use these Gauss laws in various cases. Any questions before you go for a break? Okay, see you after 10 minutes.